This physics question is about an angular momentum of a merry-go-round. And so the information given to us is that the angular velocity of the merry-go-round is 0.7 radians per second. The radius of it is 15 meters. The mass of the merry-go-round, I just have mass of the merry-go-round denoted m subscript m, like this. That's 750 kilograms. And the mass of the boy is 45 kilograms. So that's information that is given to us. So the first question asks us to find the inertia of the merry-go-round. So in order to do that, we would use this equation, the inertia of a disk, because when you think about it, looking at it from the top, that's basically what a merry-go-round is. It's just a disk, and it spins from a center point from, around a pole. And so we can treat it like a disk, and we would therefore use this equation. It's 1/2, I just denoted it 0.5 to make it seem a little easier, times mass times the radius squared. So we have 0.5 times the mass of the merry-go-round, that's 750 kilograms, times the radius of the merry-go-round, times 15 meters squared. So, and we would get that answer in kilograms times meters squared. So that is the inertia of the disk, or the inertia of the merry-go-round. That's what this means. So then we want to find the inertia of the child on the merry-go-round. And we are also given that he is 4 meters away from the center of rotation. That's where he jumps on. So the inertia of the child can be found by using this equation, the mass times the radius squared. We do not use this equation, the 1/2 times mass times radius squared, and that's because the mass of the child is concentrated only at that point, as opposed to the mass of the merry-go-round, or the disk, so to speak, which is uniformly distributed in the circle. So if you think of a merry-go-round, it's just a big circle with, essentially a pole through the center at 0.5 at the center of mass. So that's why we don't have the 0.5 here, but the rest is the same. And so whenever we plug those values in, 45 kilograms for the mass of the boy, and 4 meters squared for the radius, or where he jumps on the merry-go-round, we get this value in units of kilograms times meters squared. So the last question asks for the final speed of the merry-go-round once the child jumps on it. So in order to do this, we know that the angular velocity initial is going to equal the angular velocity final. And that's because in this question, angular momentum is going to be conserved. So in order to find the angular momentum of this system, we have to multiply the inertia times the angular velocity, and that's of both the merry-go-round, or the disk, and the child. So we would multiply the inertia of the merry-go-round times the angular velocity initial of the merry-go-round. So this is the initial portion of the system, so that's without the child on it. And we would set that equal to the final angular momentum, which is equal to the inertia times final angular velocity of the system. But for the inertia, we have to add not just the inertia of the merry-go-round, but we have to add the inertia of the child, because in the final portion of the system, the child is included. And the child doesn't have an angular velocity, but he does have an inertia, and that's why we would add that to the inertia of the merry-go-round, and then multiply it times this, as directed by this equation. So given this equation, we would plug all of our values in, and we want to know what the final angular speed is for the merry-go-round once the child jumps on. So we plug everything in, and this value, these two numbers together, they add up to become this number, 85,095 kilograms times meters squared. And so we would divide both sides by that value in order to separate this, the angular velocity final, by itself. And so that gives us a value of 0.6941 radians per second as our final angular speed once the child jumps on.